So in this series of videos in the chapter of linearly dependence, we still did not define what are dependent or independent set of vectors. So let us answer to that question. So let us say we have a set of vectors v1 to vm. They are called dependent or independent according to the vectors here. So if v1 to vm are linearly independent vectors, we say that this set is a set of independent vectors. Okay. Now, since this is linear algebra, we are presuming that these sets are finite. Okay, but of course we can have a set with infinite vectors. Okay, if they are infinite, okay, but you have a set of a subset of dependent vectors, so let us say v1, v2 till vk are dependent. If these are dependent, so a subset of an infinite set or an infinite set has a subset of dependent vectors, well, we say that S, let's call this S, is linearly dependent too. Okay, so that goes for infinite sets. Now the empty set is a convention, or is defined to be linearly independent. I don't know if everybody agrees with this, because there are some odd linear algebra books, but okay, I'm going to use this definition. Okay, I'm going to define the empty set as linearly independent. Okay, some other, let us say, properties. Let us say we have a set of vectors v1, v2 till vm. And let us say we have two of them are equal. So let us say that, for instance, v1 is equal to v2. So then, of course, these vectors will be linearly dependent. Okay, because if v1 is equal to v2, that means that v1 minus v2 is the same as v2 minus v2. So v1 minus v2 will be the zero vector. Okay, so in this set of vectors we will have v1, right, minus v2 here, right, plus v3 plus v4 plus etc. plus vm. Okay, and the coefficient of these ones can be 0, this one can be 0, this one can be 0, this one can be 0, the scalars, and you will get, and this one is not 0, the scalar here is not 0, the scalar here is not 0, but here you are going to get the zero vector for this reason, right? So adding all these vectors, you will get the zero vector. So that means that this set v1, v2, vm, right, is linearly dependent. So if any two vectors of a set are equal, then the set will be linearly dependent. let us say we have vector v1 and we have vector v2, okay, and if I multiply v2 by a scalar in the field, I get v1. So this one is a multiple of this one, right? They are multiple of each other. Well, if they are multiple of each other, then these two vectors will be dependent. Okay, so multiple vectors, let me write, multiple vectors mean that they are dependent. Okay, and if they are dependent, it also means that they are multiple of each other. Okay, the proof is well, I can provide a proof for this. Okay, let me pick, for instance, this one first. Okay, so let us say they are so I'm going to prove, yes, let us say they are dependent. So dependent vectors are multiple of each other. Okay, so let us say that v1 and v2 are dependent. Okay, so if that happens, so a times, there will be scalars, a times v1 plus b times v2, where you will get, since they are dependent, you will get vector 0. Okay, and not all of this will be 0. Okay, so let us say that a is not 0. Well, if a is not 0, this means that so I'm going to write v1 here will be written as minus b over a, right, times v2, right, because v2 will get on the other side. Okay, well, but this means that they are multiple, right? So if they are dependent, that means they are multiple. Okay, so it's proved on this side. Okay, because this will be your new k, right? So v1 is your new alpha. Okay, let me prove on in the other direction now. So okay, in the other direction, so let me prove that multiple means they are dependent. So the vectors are multiple of each other, right? So v1 can be written as k v2. Okay, but if that happens, then v1 can also be written in this way, right, where the scalar here will be 1. Okay, and this means that this means, since they can be written as 0 vector without the scalars being all 0, okay, this means that they are dependent. Okay, and that concludes the proof for both directions.